Hello everyone. The topic that we are going to study today is oxidation number, which is under the chapter Redox, class 11th chemistry, which is in your part 2 textbook, right? Okay. Now let us understand what is oxidation number from the very beginning, right? Basically, it is a real or an imaginary charge on a particular atom in the compound. So how is this charge developed? Let us, take an example. So we have hydrogen and fluorine bond here. Now you all tell me which is more electronegative. Is hydrogen more electronegative or is fluorine more electronegative? So we all know that, fluorine, it is the most electronegative element in the periodic table. So due to this, the lone pair of electrons, basically, sorry, the shared pair of electrons, it shifts more towards fluorine, right? Because fluorine has high electronegativity, right? Hence, this leaves us with a charge of, like a partial positive charge of +1 on hydrogen and -1 on fluorine because the electron is getting transferred towards fluorine, right? Okay. Now, so this is what is creating the charge. Now, fluorine would have like a oxidation state of -1 and hydrogen would have an oxidation state of +1. Let us see the rules of calculating the oxidation number. So the rule is the elements which are in free or uncombined state, each atom, it bears the oxidation number of 0. Okay, each atom will have 0 as the oxidation number. Okay, like H2, it is in free state, right? Okay, so it will have 0 oxygen because both the sides, the element is the same, right? So there will be no attraction of lone pair, sorry, the shared pair of electron towards any atom. The shared pair of electrons will not move, it will stay stationary, right? Because both the atoms are same. So in the free state or the uncombined state, each atom has the oxidation number 0. So you can see in all of these cases, we have the same elements like phosphorus, sulfur, oxygen, right? So in these cases, the oxidation number of these elements, it is 0 because they are pure elements. Okay. Okay. So the second rule is, okay, oxidation number is nothing but it is equal to charge on an atom. Like sodium, we know the charge is +1. Why? Because it loses one electron to become stable, right? So charge is +1. So it becomes Na plus. So the charge is only equal to the oxidation number. For magnesium, the charge is +2. The oxidation number is equal to +2, right? Okay. Like chlorine gains one electron, right, to become stable. So the charge is -1. So that -1 is the oxidation number of chlorine. I hope you have understood this. This is the second point. Next. So oxidation number of alkali metals, that is the first group is +1. Alkali earth metals is the group 2 is, +2. Okay. And the aluminium, because aluminium is in group 3, right, or group 13. So all of the atoms in its family is aluminium family is +3, right? Okay. So oxidation number of oxygen is mostly it is -2 because obviously it is in, group 6. So in group 6, it needs 2 more electrons to become stable, right? So usually oxygen has a charge of -2. But then it also depends that oxygen is bonded with which elements, right? So here, obviously, the lone pair of electrons would be, the electrons would be shifted more towards oxygen, right? Here. Okay, so hence the charge would be +2 and here the charge would be, sorry, -2 on oxygen. And hydrogen, it is +1 and here also it is +1, right? And overall, see, overall the atom, the compound, it should be neutral, right? See, oxygen has -1, -1 and -1, that brings it to be -2 and hydrogen has +1. But in case of peroxide, like we have hydrogen peroxide and in case of Na2O2, what is happening? The charge becomes -1, right? Why it is -1? Because here, see, here so oxygen is there. So here there will be no pull of electrons, right? Only pull is from here. So this oxygen will attract the shared pair of electrons towards itself, gaining a charge of -1. Hydrogen has +1. Again, this oxygen has -1. This has +1, right? Okay. So the reason is also mentioned to you here. The electrons, they're shared properly, right? There is no shifting. Okay, there's 0 charge here. On this side, you can see it is -1. So I'll just erase it so you can see it very properly, right? So in case of hydrogen peroxide, that is H2O2, the charge on oxygen is, -1. Hence the oxidation number is -1. Okay. In case of superoxides like KO2 or RbO2, it becomes, -1/2. Okay. So let us understand now the next rule. So O2F2, again, it is +1. Why it is +1? Can anyone tell me? Can any one of you try? So basically, fluorine is more electronegative. So this time, fluorine will attract the lone pair of electrons towards itself, right? Right. So fluorine would gain a charge of -1 here. So oxygen will become +1. Here also, fluorine would gain the electrons and become -1, and oxygen will become +1, right? So we need to see also, in case of oxygen, that it is bonded to which element, right? Okay. In case of OF2, it is +2. Why? Because oxygen is bonded to two fluorine atoms, right? So obviously the shared pair of electrons is more towards fluorine here. So fluorine here is -1 and here also -1. Here it is +1 +1 together, making it to be +2, right? So if you can see the image, you can see +1 and -1 written over here. Okay, now I'm moving forward. The next is hydrogen. So hydrogen is mostly +1, as you have seen previous examples, because mostly other elements are more electronegative, right? But when we have like lithium hydride or NaH or CaH2, in these cases, hydrogen is more electronegative, so hydrogen gets a negative charge, right? Okay. So basically all the halide ions, they have a charge of -1 because they gain one electron to become stable, all of the halogens, right? So we need to remember actually these charges to be able to solve these type of questions, okay? So let us see. Okay, now we want to calculate for this chlorine. Okay, okay. So for hydrogen, we know that it is +1. Chlorine, we do not know. I'm keeping it as X. So in general, we know that oxygen has a charge of -2. Only in certain cases, when it is hydrogen peroxide H2O2, when it is combining with fluorine, okay, then is the charge would change. Otherwise, it would not. So it is -2. So -2 into 4 is equal to 0. Because at the whole, can you see the compound is neutral? So I'm putting is equal to 0. So 1 plus x minus 8 is equal to 0. So x minus 7 is equal to 0. So your x is equal to 7. Right? So your oxidation number of chlorine is 7. So this is how it is 7. Okay? That is a positive oxidation number. Okay. So for a compound, the algebraic sum of all the oxidation numbers is equal to 0. So you can even check it here. It is coming out to be 0, right? So this is how you can check if your oxidation number is correct or not. Okay, for a polyatomic ion, the algebraic sum of oxidation number is equal to charge. Okay, let us understand. So we have CO3 2 minus. So here, suppose what is the charge on carbon atom? So charge on carbon atom plus the charge on oxygen atom is equal to the overall charge. So charge on carbon is +4, right? Now one oxygen has a charge of -2, so 3 will have a charge of -6, right? So 4 minus 6 is equal to -2. Hence, if there is a charge present on the top, then all the oxidation numbers should amount to that charge, okay? So, usually metallic elements, they have positive oxidation number. Non-metallic elements have negative oxidation number. Transition elements have several positive oxidation number. Okay. So this you will study in detail in class 12th when you go. There is a chapter called DNF block elements where we'll study the reason, why transition elements have like a variety of oxidation states. So these are some oxidation. See, sodium is in group 1, so it has +1, right? Magnesium has +2, aluminium +3, silicon +4, phosphorus 5, 6, 7. Usually, like phosphorus, the highest oxidation state is +5, which is equal to the group number actually. These group 13, 14, 15, 16, 17. They're also known as group 3, group 4, group 5, group 6, and group 7, right? Okay. So as we move from left to right in the periodic table, the oxidation number increases. Okay, let us work. Okay, let's see this. Okay. So basically in this example, we are going to see that, if oxidation is taking place or reduction is taking place. Let us calculate it together. But how can I calculate it? Only if I know how to find out the oxidation number. Okay, let me work out for copper. Here I told you in pre-state it is 0. Okay. Let us understand for copper over here. So I don't know what is the oxidation state of copper. There are two copper atoms. I'm taking it as 2x, right? Okay, one oxygen is -2, which is equal to 0. So 2x is equal to 2 and x is equal to 2 by 2, which is equal to +1, right? So it is +1 to 0, it is moving on here. So 1 to 0, that means it is gain of electrons, right? Gain of electrons is called what? Reduction. So let us calculate for sulfur here. Let us calculate here for sulfur. Okay, let us calculate first here. So sulfur is x minus 2 into 2 is equal to 0. So x minus 4 is equal to 0. So sulfur here is equal to +4. +4. Okay. Here, sulfur. See, copper, the usual oxidation state is +1. So two copper atoms are there. So 2 into 1 plus x is equal to 0. I don't know sulfur, so I'm putting x. So 2 plus x is equal to 0. X is equal to -2. So sulfur going from -2 to +4 is like a loss of electrons. And loss of electrons is what? It is oxidation. Right? So hence it is given here also. I will just erase what I have written, C, right? And so you can make out that, what is reduction, what is oxidation based on the oxidation number. So I hope you have got it, how to calculate the oxidation number. Okay. Now let us move on to, the redox titrations, which are very easy titrations. So this you must have done in your laboratory. Basically, this is a method to determine the, what is causing oxidation or reduction. Okay. For example, we have oxidant in the volumetric, in the burette. So, and then reductant you take it in the beaker. Okay, and we put certain indicator. Let us take an example. What is an indicator? It is the indicator is a substance that changes color in an acidic or a basic medium. Let us understand how it happens. Okay, so when you are doing okay, so these are the examples that we are going to study today. I am definitely sure you must have done this titration with potassium permanganate, okay, which is a self-indicator. So this is an oxidant and this is a reductant. Oxidant is the one, that is acting as an oxidizing agent, right? So when we add it, so this is the equation that you can see. You can compare the charges like who is getting oxidized and who is getting reduced over here, right? So the titration helps us to find out the, what amount of KMnO4 is required to reduce the amount of the reductant here. So this would help us to find out the amount of KMnO4 required to reduce the amount of reductant, because this value over here is fixed, right? Okay. So this would give you pink color at the end point. Next is potassium dichromate, which is not a self-indicator. So we add, diphenylamine or diphenylbenzidine as an indicator. And here also you can calculate it with the help of, this reaction. What is happening? Oxidation, reduction. So basically this is a very good oxidizing agent. So with the help of the reaction, we can calculate that, how much amount of this K2Cr2O7 is required to, completely reduce the, the reductant that is present over here. Okay. So end point is an intense blue color, right? Which you get by adding diphenylamine, which is needed because it is an indicator. Then we have, okay. Okay, so if we would see this, if you have a Ki solution, potassium iodide, if you had copper 2 plus into it, right? So what is happening? Let us check. Copper is in 2 plus state over here, and let us see what is the state of copper here. Okay, so we know that all halogens are like minus, right? So 2x minus 2 is equal to 0. So 2x is equal to 2 and x is equal to 1. So here copper is in +1 and here it is in +2. So +2 to +1 is what? Oxidation or reduction? Yes, it is reduction. Okay. Okay, it has gained 1 electron. What about this? Here iodine has a charge of -1. Okay. I minus, and here it is 0. So -1 to 0 is what? Loss of electrons. So oxidation, right? So basically, copper here is acting as an oxidizing agent. Who is helping this iodine to get oxidized? Who is taking the electron of 1 electron of this iodine so that it can get oxidized? It is copper, right? So this is how we can do redox titrations, right? Okay. So with the help of starch, we can see the color change. So iodine gives an intense blue color with starch, right? So this is again another example of a titration where we have sodium thiosulfate and copper in the beaker. Oxidation is taking place, copper plus Ki solution, right? So this is the reaction equation where you can calculate the oxidation states and check for yourself. Okay. So thank you so much. I hope you really understood what is the importance of the oxidation number, as it helps us in redox titration. It helps us to, find out whether reduction is happening or oxidation is happening. If you want to, study this chapter in detail, we can do it through Urban Pro, right? Okay. Thank you so much.